All right, let's get started. So the lab today is not that difficult, but there are two things you need to know. First, the resistors are being fabricated in the N well. We haven't covered that yet, but let's take a look at that. What's the N well? But you have learned logic, and you know the PMOS, the P plus are being fabricated in, being doped in the N well. So if this is a cross-sectional view of the device, and this is a P substrate, always being grounded, right? And there can be, you can fabricate a N plus material, but it's not super dense like the N plus, but it's still N material being doped into the silicon, into the P substrate, okay? So it's called N well. And after that, you can have a little PMOS, P plus here. So that's a P active in your electric VLSI. It's called P active. So why not just directly have the P plus being doped in here? Why do we need an N well? Yeah, the P sub is being grounded. If you have a P plus being doped into the P substrate, it's the same material. If you ground the P sub, you are grounding the P plus as well. All right. And because the N well is called tub, right? If you have seen some other tools, they also call this a tub. It's a 3D structure. And if you look from the top, it looks like a bathtub. It's tiny, okay? And you can define the size of the N well. There's an option in the library in electric VLSI. You can directly grab a N well node and right click and change the property, for example, the width and length of the N well. So you can totally define it. But there are some specific rules regarding N wells in different technologies, like in C5, the N well cannot be, so there are rules for width and length of the dimension of the node, the smallest node. Right? You can make it huge, the same size of the chip. It's just a huge N well. Doesn't matter. It's pretty easy to fabricate the huge one. But for small ones, there are rules to define the sizes of the width and length. Okay, for the N well. We are going to use N wells as a resistor in the circuit. So what's going to happen is if you look from the top, okay, so this is a cross-sectional view. This is top view. So here's the N well. If you look from the top, it's probably just a N well like this. Right, and in the middle there's a P plus. So I make a cross-sectional view here, across this line, and I look from the side, I'm gonna see this, for example, all right? Because this is a 3D structure, from the top you can see it's a rectangular shape or a square shape, whatever. It's just an area of N wells. And from the cross-sectional view, you can see it's going inside the P sub. So it's definitely a 3D structure. It's a 3D shape. And you cannot control the depth of the N well really much. And remember, the resistance is this times L over A, right? So this is the resistivity, which you cannot change because that's the material's property. And this is the length. This is the area, cross-sectional area. You'll still remember this in physics, probably. Is this the resistor? The resistance of the resistor? Resistivity, and times this over this is the resistance of the resistor. But when you learn this in physics or in circuit 1, you are dealing with what? Like wires, right? You don't actually care about the width. You only care about the length and the cross-sectional area, which is the diameter of the wire. And but here, you see that you can modify the width and length, but you can now modify the depth. So in this case, we do not care about the only the length or only the width. We care about how many squares it has. It changes in the specific ratio. If you have a little square like this from the top, that's the top view, and a larger square like this, so these two guys have the same resistance. Only when you change only one direction, only one dimension, you actually change the resistance will be changed. But if it's a square or it's changing in a specific ratio, the resistance is not going to change. Given that the depth of the N well is not changing, you always dope the piece up with the same depth. Okay, this is for the wires. Don't think about this right now, but only look at N well. When you are doing the layout, you grab a little N well node, and you can directly just change how many squares it has to change the resistance. So the fundamental unit here for the resistance is how many ohms per square. Doesn't matter how big is the square. You just care about the resistance per square, because it doesn't matter it's a big square or smaller square, you always have the same resistance. So the parameter here for the C5 fabrication process, it is about 800 ohms per square. 800 ohms per square. So if you need a 10K resistor, wait, which is a sheet resistance? Is that 800 ohms? Yeah, it's 800 ohms. All right, so that's it's called sheet resistance, or how many ohms per square, right? So it's some around 800 ohms. And another thing you probably, if you are not in analog, you didn't hear about it in the past. Lambda, because C5 technology is defines the smallest size of every single transistor is 500 nanometers. So in order to do the layout easily, we do not measure every single transistor individually. So we just directly use a scale, which is 300 nanometer. We have mentioned this a few times. So 300 nanometer as a scale, or it's called lambda, is 300 nanometers. And it's a C5 technology, means the smallest node or smallest length of every single transistor is 500 nanometer in theory, you know, but we do not use 500 nanometer for the smallest feature, because it's just a theory. We want to use something a little bit bigger than that. And if we pick up lambda to be 300 nanometers, and we use 2 lambda as the smallest, so you are getting actually 600 nanometers for each as the smallest dimension of the transistor. Okay, if you are using, for example, for the C5 technology, 1 lambda is 300 nanometer, and we never fabricate a NMOS which is 1/1. The width over length is 1/1. We never do that. because this 300 nanometer is not, it's a scale, it's not the smallest fabricatable size of this process. Keep in mind, the smallest lens will be 600 nanometers for the for one transistor. We always use lambda in electrical VLSI. So whenever you are looking at the numbers, you directly pick up like 10. 10 doesn't mean it's a 10 micron or 10 nanometer. It means 10 lambda. So it's actually 10 times 300 nanometers, which is 3 micron. Remember? Okay. Let's take a look at here. See, I have a width to be 15, length to be 187.5. So these are lambdas, right? 15 times 300 nanometers. It's not 15 micron, not 15 nanometer. All right. How do I calculate it? How do I get these two values? Let's read this one more time. Sheet resistance, well, 800 ohms, the minimum width. So, because the C5 technology has a specific rule for the size of the NWL, okay, and you can see the minimum width of every single NWL is 12 lambda. So it's 12 times 300 nanometers, right? That's the smallest feature. Doesn't matter it's a width or length, right? The smallest edge of that well will be 12 lambda. And we need a 10K resistor because the 12 lambda is the smallest in theory. And what I picked up here is 15. It's a little bit larger than 12. So now I need to calculate the length to form a 10K resistor. Think about it. So 12 lambda, let's think about it. 12 lambda, for example, 12 lambda is the smallest edge. And I picked up 15 lambda. Okay. For example, this is 15 lambda as the width of the 10K resistor. And I need a 10K. I need a 10K. So the entire resistor should be 10K. And the sheet resistance is 800 ohms per square. So what should I pick up for the length? Which number should I use for the length? It's 800 ohms per square, right? It's 800 ohms. 15 lambda, 15 lambda, right? This piece is 800 ohms. And I need a 10K in total, which divided by which? So I can get how many lambdas for the length. Remember, it doesn't matter how big is the square. It's going to be 800 ohms per square. That's called the sheet resistance. I grab every little square, it's going to be 800 ohms. And now I picked up the width to be 15 lambda because it's a little bit larger than 12 lambda, which is the minimum width for any NWLs in the C5 technology. So this is already given. And because I know every square is 800 ohms, so I just form a square by myself. I just draw a line here, so I know this is going to be 800 ohms. And since all the resistors are being connected, it's just one piece. But you can imagine that all these little squares are being put together in series. So they're actually being added together. And you need a 10K ohms in total. And every square is this much. So if you use 10K over 800 ohms, and this means how many squares you need for this NL. And I think the result is somewhere around 100 10K over, let's do it. $12.5. $12.5 squares. So we need a 12.5 this. So how many lambdas? That's the length, which is 187.5 lambdas. And every lambda is 300 nanometer. So it's going to be this times 300 nanometer will be 1 10K resistor. I have to think about one thing, because resistors and capacitors are not, normally they takes a lot of space on the chip. So before you lay it out, make sure it's not too long. You know, the die or the C5 technology, the little silicon die, is only 1.5 millimeter. If you have one straight resistor which is longer than that, then it's going to be a disaster. You couldn't fabricate it. You have to turn it at some point. You know, you cannot directly just make one long resistor. You have to do this. You know, to save space. Serpentine shape. Let's verify it really quick, see if it's longer than that. I'm pretty sure it's not, but let's calculate it. So this is 187.5 lambda, and per lambda is 300 nanometer. Let's just times 0.3 micron. So it's 4.5 watt for the length of every resistor. 10K resistor, what's the length? 4.5 micron. Because I used this one times lambda, which is 0.3 micron. Wait, is that right? Seems like it's not right. 187.5 times 0.3, boom. Okay, so it's 56.25 micron. And 1.5 millimeter means it's actually 1500 micron for the die. So one single resistor is only 56.25 micron or micrometer. So it's going to be something like this, even or even smaller. Doesn't matter. It's not affecting too much. That's fine. But if you need a lot of these resistors, you need to think about how to shape it. So like what I have here, you know, I just put them in parallel and then make the connections like this to save space, because you definitely don't want to just have all the resistors just trailing the first one. You know, it's going to be a very long resistor eventually. So make a serpentine shape. Here's another trick. If you look at the ladder, let me show you really quick. If you look at the ladder like this, definitely you can have the resistor schematic which you already built last week, and you can have the 10K resistor layout, like whatever I just told you, the length and width, just place it and change the length and width in the layout view for every single 10K resistor in the layout view, and you make the connections, and you export every single bit here, and then you're done for the layout, and then you do LVS to compare the schematic and layout, and you're done. But that's not the best way to do it. Remember, this is a very typical example for making different circuit blocks or different hierarchies in your IC design. It's a very simple example, but it's really classic, I can say. Since you can see that, you can definitely, in the layout view, just place all these resistors in one schematic, and then run the matching check, which is LVS or NCC in electric VLSI, which is doing the schematic and layout match check. But that's not ideal, because if you, for example, if there's a little mistake you made in the layout view, but you spend a lot of time to place all the resistors together to form this huge resistor string, and you have to fix everything, go back and fix everything one by one later if you see problem. It's not matching with the schematic. I mean, if, right? So if it's not matching, eventually you find it. After 2 hours, you do a schematic check, it's not matching. And you have to go back to the layout view and change every single one by yourself, and one by one. So the better way to do it is starting with smaller cells, smaller subcells. Because you can see that this guy has this substructure is being repeated all the time. If you are trying to complete all these like 20 resistors at the same time, it's probably not 20, I'm just saying, if it's 20 resistors at one time, it takes maybe 10 times longer time than you just make a 3 resistor little subcell. So just spend 10 times less time to make this guy and make a subcell out of it, and then start another schematic, just directly drag and drop this subcell to form a bigger cell. Because you can do a schematic check for this subcell really quick. If you see the problem, you can definitely come back and fix it really quick. Okay, if you know if this one passes the schematic check, and you use this subcell to form a bigger cell, and you get a way greater chance to pass a schematic check eventually. You know what I mean? You definitely want to start with subcells, small subcells. Super important, right? Especially in the future. I mean, you have when you are building these LUs, build something like this, and you do not have subcells. You have one schematic, and then you start laying it out. It takes 2 weeks to lay it out. And after you are done, oh, I'm done. Just finish the layout. Let's go party. And you press the little key L to do the NCC check, and boom, 2,300 errors. Everywhere. You probably want to drop out during the last 2 weeks of the semester. I cannot pass this class. Just want to drop. All right, definitely do subcells, right? Just for example here, when you are looking at, for example, this mux, this multiplexer, I have all different levels of subcells in only this part, not mention the entire thing. in this little multiplexer, I have a multiplexer as a highest hierarchy, and I have a little inverter as a subcell, very bottom level subcell. I did a lot of LVS and DRC check with this little inverter. I know it's going to work. So I directly drag and drop into a schematic of the multiplexer, right? And also every little thing here, I forgot what the gate is. It can be a AND gate or OR gate, doesn't matter. Okay, it's a totally different subcell, and I know it's working, so I can directly drag and drop to the scheme to the layout when I was making this multiplexer. I know it's working. I know that subcell is working, so I just grab it and put it into this layout view, and then eventually I can form a bigger layout, which is this multiplexer, and then I do a schematic check. Boom, probably only 2 errors. Easy to fix, just 2 errors. I just find out and fix it. Okay, then the multiplexer is done. So I know the multiplexer is ready. So the multiplexer here is one subcell. I know it's ready to use. It's just sitting in the library. I'm gonna use it at one moment in the future when I'm forming this ALU. So later on, if I need it, I directly drag the entire subcell of the multiplexer to this layout view, okay, and put it here and make the connections. It's the same as all the other ones. I just have to do it one by one. You need to have all different levels of subcells. Very critical. So that's the first time you are going to test this kind of strategy and try to use all the different hierarchies and levels and subcells. Definitely do it, and you will see. Probably when I'm talking about it, you cannot feel like why it's so important, but when you are doing it, you will be able to tell. And another benefit of doing this is it makes the so here's a subcell, right? The 3 resistor subcell. I have 3 ports. So and I also made an icon out of it. So the icon is like a chip, has all the pins available for this little structure. See left, right, down. So that's a 3 resistor box, black box. And I can use this one to build the schematic of the R-2R ladder like this. See? Make sense? Okay. And you do not have to place every single resistor in here. Sometimes they're misaligned. They are longer wire, shorter wire. This looks totally a mess. But if you have a black box, every box is identical, since you know that. It's the same subcell. It's the same theory for, here's one more thing I want to let you know. For the R-2R resistor, since they are all 10K resistors, you need a little 2R here. It's R2Rs. It's 2R, but you have 1R is missing, so you just need to add another resistor. Doesn't matter. It doesn't have to be in the box. Add a resistor in there. It's same for the layout. Same for the layout. Because you are doing schematic and layout matching, checking. So if you have a 3 resistor schematic, you need a specific layout to be matched with that schematic. So you need a 3 resistor layout as well. So this is an NWell resistor string, has the left, right, and down, like this. And also make an icon out of it. Wait, no. You don't need an icon from layout. You don't need an icon from, this is not an icon. This is something, after you are done with the layout, right, you go, directly go to the R-2R ladder, upper level layout view, okay? And you want to use this part in the library, you left click and hold it and drag and drop to your new layout view. So you can see a box like this. It's not showing you all the details inside, but you can click the little eye here, this little button. It's going to make the inside structure visible. Even though they are all the NWells are visible in here, they are not clickable because it's on a higher hierarchy. it's not at the bottom level, so you cannot modify it, which is good. So you're not changing anything in there. You can choose to see it, or you can choose to not see it. Doesn't matter, it's your choice. So just place all these different layout blocks into your new layout view, which is the actual R-2R ladder. Like this, just place them on the top of each other. And you can use a array function, but you don't have to. Not too many, right? Not too many. And don't forget the very last one, the little 10K resistor at the very bottom, like little tail here. Okay, and this is schematic. Remember, in electric VLSI, we don't actually do simulation with with a layout view. You can definitely do it. It's not going to change anything. The result will be pretty much the same. We only need to do schematic simulation here in this class because you already have assume you already have the LVS or NCC passed, which is a schematic and layout matching, right? The EDA software only extract the electrical net list, so it's actually just reporting all these nodes. It's the same electric net list for the schematic and the layout, so it doesn't matter which one you are going to simulate. Yeah, it's the same stuff. So as long as your NCC is you can pass the NCC, so which means the schematic and layout has the same electric net list on the backscene, and you can directly just simulate the schematic. These are totally the same net list. You don't have to do it again with the layout. So you can directly have this schematic here and run the simulation. So this icon is different from the schematic you used last week. Keep in mind, last week you just placed all the individual resistors to make out the string, but here you have subcells. So this must be a new one, must be the one you made in this way. Blocks. Okay, and you have to do it because this is the only way you can match with your layout. Because in the layout view, you are doing 3 resistor blocks, so it has to be 3 resistor blocks here as well to match with the ports. Make sense? Any questions by far? No? All right. Okay, you can start working on it.